So I wanted to use this video, short one, to fix some of the mistakes, both intentional and unintentional mistakes that I made in prior videos. So here's an unintentional mistake, one that I should correct. I think I said something like radioactive decay events are more likely as time passes. This is nonsense, right? It's just as nonsensical as saying that flipping heads is more likely as time passes, right? The probability of flipping heads on a coin is the same no matter how much time you let pass. And similarly, the probability that an atom will decay is the same no matter how long you wait. And let me be more precise. The probability that an atom will decay in some next time period is the same, assuming of course it hasn't decayed, whether you measure that probability now or you do it in an hour, again assuming that it hasn't decayed, right? It doesn't matter when what time slice you look at. If it hasn't decayed, the probability that it will decay in the next 5 minutes is the same. And 5 minutes is not what's important here. You could also ask the same question about what's the probability that it decays in the next hour. Same thing. Okay, so I wanted to correct that. But what is true is that even though the sort of chance of an atom decaying in the next moment or in the next time slice is the same no matter what, as more time passes, you're going to have more of those time slices. In other words, more chances for that event to occur. Okay, so that is true. Okay, the other thing that I wanted to talk about was this radioactive tracer problem. So here we said that, and I want to focus on this kidney part of it, that we said that kidneys would remove 20% of the tracer present every hour. And I kind of cavalierly wrote down this term in my differential equation and said some words which I guess were convincing because nobody came back and corrected me on this, that this was correct. Okay. In fact, it's incorrect. Okay. And I want to make sure that we understand this. What's the correct way of thinking about it? Well, if the kidneys are removing 20% of the tracer present every hour, okay, this does suggest that there is a constant of proportionality that we need to be thinking about. That, in other words, the rate of change, dn dt, and this is just for the kidneys now. I'm focused only on the kidneys, not on the radioactive decay aspect. This is going to be equal to some constant k, negative again, times the amount of radioactive tracer present. So negative kn again. And we know how to solve this. This is given by n of t equals n naught times exp of negative kt. Negative kt. Yeah, sorry. The question is, what's k? And I was very, again, cavalier in saying that it was 0.2. But please observe, what are we really saying with this 20% figure? We're saying that every hour that passes, the amount of tracer that vanishes due to decay is 20%. So we're kind of talking about n of 1 hour. N of 1 on the one hand is equal to 0.8 times n naught, because 20% of n naught has decayed. So it's 0.8 n naught that's left after 1 hour. On the other hand, we know from the solution that n of 1 is equal to n naught times exp of negative k times 1. Negative k times 1 is just negative k. So then we can set these things equal to each other and then solve for k. Maybe I should go ahead and do that. If we do that, I think we get that 0.8 is equal to exp of negative k. 0.8, by the way, is 4/5. So we get the natural log of 4/5 is equal to negative k. So multiplying both sides by negative 1 and remembering the rule for logarithms, this tells me that k is equal to the natural log of 5/4. Okay? That's our k. And so in particular, this 0.2 right here is incorrect. The contribution by the kidneys should be, oh no, should be, I should erase this, and I should erase this, and I should erase this, and I should replace it by what's correct. What's correct is this log of 5/4. There should be log of 5/4 there, natural log of 5/4 there, and natural log of 5/4 there. And now this is going to be correct, okay? I think it's important for you to be really critical of mistakes when they arise and call them out. Hopefully there was maybe some kind of red flag, but so often when these red flags wave in our head, we do nothing about it, okay? It's more critical than ever that you make sure that when you are confused, you say something. Why is that? Well, it's because nowadays it's really, really easy to produce really convincing sounding and looking material. Because AI is really, really good at it, okay? And we're running into this issue big time. Professional mathematicians are receiving manuscripts from people who purport to have proven really grand conjectures that have vexed mathematicians for a very long time. Things like the Riemann hypothesis. And it might look quite convincing in that it's very professional sounding and professional looking. What it is, in fact, is AI slop, AI hallucination, okay? And we have to be able to discern what's real from what is just nonsense. Fortunately, mathematics has a very high standard for this kind of thing, and so we're not going to just accept the outputs of artificial intelligence uncritically. You need to do the same thing, but you need to take that same approach not just with AI outputs, but with all outputs, whether they purport to be human, AI, whatever. Because let me tell you, there's AI slop, sure, but you know what else there is? There's human slop, okay? There is human slop. There are people out there that are looking to fool you and waste your time, energy, motivation, your money, direct them in certain directions through deception, purposeful deception. You need to guard yourself against that, okay? So that's my message, and I'll leave it there.